This video addresses observation, inference, and scientific models. The learning objectives include be able to identify and distinguish observations and inferences in the natural world. Be able to explain how scientific models are used to bridge the observable and unobservable worlds. Be able to explain how scientists build and test hypotheses about processes that cannot be directly observed or seen. Be able to develop testable hypotheses and predictions about a scientific model. And lastly, be able to define the key characteristics of scientific models and differentiate representations from scientific models. So let's start with a question that motivates the discussion we'll be having. So which of the following statements is true? So Susan teaches and researches human biology. Which of the following is Susan using as a scientific model? This question basically asks you whether you know what a model is. So A, a physical representation of a knee joint that Susan uses in her class to explain to students how the knee works. B, a computer simulation of human population growth that Susan uses to demonstrate the rate of overpopulation in a lecture to the general public. C, a drawing of a biochemical pathway made by Susan that reveals to her new insights about an enzyme in the human digestive system. All of the above or none of the above. Well, the correct answer is C. It turns out that there's a big difference between what most people think models are. Most people think a model is just a representation of something. But it turns out that a scientific model has an important difference that we'll be discussing in today's lecture. So, observation, inference, and scientific models. Last time we talked about how one of the goals of science is to develop theories, that is, explanations for how the world works. Well, we also talked about how most processes are not observable. So if we can't see something, well then how on earth do we figure out what's going on? And we can put this another way: how can we test hypotheses about a biological process that we can't see? Well, it turns out that scientific models are the key to this paradox. That is, trying to test hypotheses about things that we cannot directly see. So the goal of building a model is basically to link the world of observations and patterns and generalized patterns, which we call laws, to the world that we cannot see. That is, the mechanisms or processes that are occurring in the world. So in the middle of this diagram you can see models. So models are sort of the glue, the bridge, the connector between all the patterns in the world, that is, what happens, and the processes, which are trying to get at mechanisms and theories about how or why things happen. So again, models are the crucial bridge between patterns and processes. So scientists then use models to bridge the observable and unobservable world. And observations and inferences are central to this process. So it's important for us to spend a few minutes just discussing, well, what is an observation and how is it different from an inference? Well, let's explore this using an observation that we see on the left. So what exactly are we seeing? So take a minute, pause the video, and think about what are some observations that you see on the left figure. Okay, well, here are some possibilities. So, do you agree that these are observations or not? There are two types of footprints. The footprints are different colors. The two types of footprints move in one direction, basically towards the right, and the two animals are moving towards each other, that is, the red and the bluish-green footprints. So, are these observations? It turns out that none of these are observations. All of these are inferences. Okay, let's try that again. So let's think about the observations and the inferences shown in this particular picture. Here are some observations. There are two types of patterns. The patterns are two different colors. The patterns have different orientations. and the patterns become closer together as we move towards the right. The inferences that we can draw from this picture is that the patterns are in fact footprints of animals. That's an inference. The animals were bipedal, that is, they had 2 legs, and were walking. Again, that's an inference. And the 2 animals encountered or interacted with one another. That too is an inference. Well, if we put together our observations and our inferences, we can basically build a model of what happened in this particular case. One of our models might be, well, the 2 animals interacted as we move from left to right, and that one of them was eaten. We can see that there's only one set of what we infer to be footprints moving off to the right. An alternative explanation, an alternative model in this case, would be that the 2 animals interacted and one of them flew away. So in this case, we're merely illustrating the differences between observations and inferences, but also highlighting the fact that these 2 forms of understanding are combined to build models of what happens in particular cases. So the key point is observations and inferences are crucial for scientists to make sense of the world, but it's also very easy to confuse an observation and an inference. Observations and inferences both make sense of the world. We couldn't understand the world without both of these. They're both very important. And observations and inferences are combined or put together in order to make a model. Well, let's use a different example to explore observations, inferences, and models. Now that we've interacted with the black box, let's think about some of the observations and inferences that we've pulled from this particular example. We can see that when the box is rotated, sounds are produced. Different parts of the box are softer than others. That is, we can press into them and it doesn't feel the same. And vibrations can be felt when the box is rotated, and the vibrations are associated with the sound. The inferences we could draw would be a metal ball is in the box. There's a ball rolling around, which explains the sounds that come out of the box. As the box is tilted, the ball rolls, which produces sounds. And in some cases, the ball's hitting cardboard inside the box based upon the sounds that we hear and the vibrations when we hold the box. So we can put these observations and inferences together to build a scientific model. And what we're showing here is the model that we've built using our observations and inferences. So we can see in the black box, our model includes the idea that the left side contains something solid, like maybe a piece of cardboard, and on the right side there's a ball that has space and it's basically moving around. So this model, clearly not the most exciting model, but nonetheless a simple example to illustrate the key features. The model, again, is an attempt to integrate observations and inferences in order to explain a system that we don't understand. So again, we're basically putting together all of our observations and all of our inferences to build a model. Now keep in mind that the model is the connection between what we hear, see, experience, and in some cases smell, and what we infer is happening. That is, we're putting together observations and inferences to build a representation of what we think is happening in order to understand that system. Well, how do we then move into the realm of science that most of us are more familiar with, that is hypothesis testing? So another way to think of this is, what exactly is the connection between a hypothesis and a scientific model? Well, it's really important to point out that hypotheses are testable statements. And what we mean by testable is that we can determine whether our statement is inaccurate or accurate, or supported or falsified. So hypotheses are then used to test if the model we built is supported or not. Clearly, we can build many different alternative models. In science, the goal is to try to understand, using evidence, what the best model is. You know, a lot of people think that science is not a particularly fun or creative discipline, which is probably the result of some of the high school experiences that students have had. But as a scientist, I can certainly say that creativity is one of the most important aspects of my job. Coming up with models and coming up with hypotheses that can test these models is a very creative, interesting, and exciting activity. Now, clearly, this black box is admittedly not the most exciting model, but in biology, we're dealing with models nonetheless. And so let me just remind you what a hypothesis is and compare it with a prediction, and talk about how we could test whether this particular model of the black box is accurate. Now, do keep in mind, this model is connected to aspects of the world that we cannot see. We cannot directly observe what's inside of this black box. So what we're trying to do is test a model of something that we cannot directly see. So let's come up with a hypothesis. Here's a very simple one, that there's a metal ball rolling in the box. That's a testable statement. We can figure out whether this is likely to be true. The prediction we could make, which is somewhat different from a hypothesis, is that the sound will stop if we put a very strong magnet next to the box. Because basically, if we think that the sound is being produced by a metal ball, and we have an extremely strong magnet, it should stop the movement of the ball when it's put next to the box. And so the prediction is, well, with a magnet, the ball won't move, and so no sound will come out. So essentially, our hypothesis test in this case is, we're going to put a super strong magnet next to the box. We're going to hold the ball in, that it will hold the ball in place. When we tilt the box, the ball will not move, and no sound will be made. So let's say we do this, and we put a strong magnet next to the ball, and we find that the sound keeps coming. That is, we had a hypothesis, and we had a prediction, and they were not supported. They were falsified. They were shown to be false. Well, clearly, the model that we came up with is not supported. So we need to go back and revise the model. It's clearly wrong. Well, one of the revisions we could make is, well, maybe there is a ball, but this ball is actually not made of metal. It's made of glass. So testing hypotheses about the unobservable world relates to the building and testing of models. An unknown system, like this black box, is explored, and we gather observations and inferences about this particular black box. We build a model of what we think is happening that is consistent with both observations and inferences. And then we develop testable hypotheses about this model and determine if they're correct. Now, do keep in mind that the building of models could take decades. Many scientists spend years and years trying to build and perfect particular models. So the cycle of building and testing models can go on and on. We can never be 100% sure that the model is accurate, but we keep trying to test it. That is, we keep trying to gather evidence in creative ways to test whether the model is correct. So models then bridge the observable and unobservable worlds. We just tested hypotheses about a system we cannot directly observe, that is the inside of the box. So again, the model is attempting to integrate observations and inferences, and it is attempting to explain the world that we experience and survive hypothesis testing. It's important to point out that scientific models are not simply representations of something. That is, our goal is not simply to represent what is inside the box. It's trying to make sense of something. So the model is a tool for making sense of the phenomenon in a manner that provides insights or more information that is currently known to the scientist. Many people think that a model is simply a representation or a replica of something that we cannot see. But that's not true. A scientific model is something that pushes our understanding forward. It helps us clarify, gain insights into how something is working. Let's see how we're doing so far. Pause the video and see if you can answer this particular question. Which statements about models are correct? Let's see how you do. Well, all these statements are correct. Models are tools that are used to figure out how things we can't see actually work. Models are used to help build theories or explanations. Models help scientists bridge the world we can see to the world that we can't see. Models allow scientists to test hypotheses about what they think is happening in the world we can't directly see, and models provide insights into a phenomenon beyond what is currently known. So models are extremely important in science. Much of the hypothesis testing in science relates to testing models. An important distinction that I'd like to emphasize is that many think that models are of something, whereas scientists understand that models are for something. This is a subtle distinction. Let's look at these two diagrams. Many people think, incorrectly, that models are depictions of scientific facts or phenomena. Well, models can be depictions, but that's not all they are. The bottom more accurately illustrates what models are to scientists and others. Models are used by the modeler, that is the person interacting and developing the model, to make sense of particular phenomena, to expand our understanding. So in other words, models are for something. They're not just of something. Now let's watch a short video to re-emphasize this very important point.
When I think about modeling, I think about describing how phenomena work. And so some things that are called modeling, which they are models when you create, for example, a 3D structural model. That's a model of something. But there's not a lot of information necessarily there in how that thing works. And so when I think about modeling, I'm always thinking about something that has explanatory and predictive power.
To bring modeling into classrooms means what we want to do is we want to help kids develop these scientific models to explain the world. Not from scratch, with lots of careful guidance by carefully sequencing the kinds of phenomena and questions that we raise about those phenomena.
All models have limitations, and so no model's ever perfect. And what students do when they're debating back and forth about modeling and their various models that they have is they're pushing each other's boundaries of what are the limitations of your model. How is that model going to work to explain the phenomena that we see before us, and how might we apply that to some new ideas or related phenomena?
So, when scientists use models, obviously their models are always tentative, and much of their interactions with their peers revolves around, the ability of their models to predict and explain the phenomena that they're interested in, right? And whose model maybe does that slightly more effectively or whatever. And so over time, through this community process, through a whole network of scientists, we arrive at more predictive and more powerful models that help us understand our world better.
And so I think modeling is a key practice that all scientists do, and that for us to Not include that as an everyday kind of experience in science classrooms would do a disservice to our students.
So a key point about models in science is that they're very, very important tools that allow us to do many things. And much of science actually involves model building and testing. That's what many scientists do in their careers. Models help scientists build explanations for natural phenomena that cannot be directly observed. Again, if we look at the diagram below, we can see that on the right hand, processes or the mechanisms that cannot be directly observed are linked to theories. And these processes and theories are represented and linked to the observable world through models. So models are more than just representations of the world. They help us move beyond what is currently known, and they help to link what we see and experience in the world and what we cannot directly see. Well, in closing then, how do we know if a model is good? Well, first of all models need to account for the data at hand. That is, models cannot ignore any aspect of the world that we know to be truthful. They must accurately predict the results of future tests and be consistent with prior knowledge. That is, they have to build upon what is known and be logically consistent. And most importantly, they have to advance our understanding and provide more insights into a phenomenon that is currently known. So this lecture basically summarized how observations and inferences are put together to build models, how models represent the natural world, but models must be tested and evaluated for their accuracy. Models are a way that scientists begin to build explanatory accounts of the world, which we reify or revalue in the idea of theories.